Thank you, and welcome to our seminars. Hope it's going to be an exciting year. So I want to talk about some work with Jeff Pennington, who will be arriving here in a few months, which has appeared recently, and I'll also talk about, if I have time left, I'll talk about a follow-up paper, which hopefully will appear fairly soon. And what I want to discuss is entanglement wedges. I want to talk about how we think of them. A lot of the focus about entanglement wedges has been on figuring out what is the correct prescription for the entanglement wedge of a boundary region. So you have ADS-CFD, maybe you have access to this boundary region. And then historically, what first happened is that Ryu and Takeyanagi, in the case where this is a static region, made a proposal for how to compute the entropy of the boundary region. Let's call this boundary region B, by as the area of this minimal surface. Okay, so you find a minimal surface that's anchored where the boundary region ends, and you compute its area. And that computes this von Neumann entropy of the quantum state of the boundary region. And then this was sort of slowly improved. So Hubini, Ryu, and Takeyanagi, Hubini, Rangamani, and Takeyanagi gave a covariant version of this prescription where maybe there's a lot of time dependence in the bulk. You still have some boundary region B. And now how do you find the appropriate surface whose area you're supposed to compute? It can't be the smallest area surface, because you can always make really small areas in Lorentzian geometry by wiggling a surface up and down. So instead, it turns out that it's the extremal surface. I think more properly it should be called the stationary surface. It's some surface in the bulk such that variations of the area vanish to first order. Okay? And if there's several such surfaces that are all homologous to B, then you take the one with the smallest area. So that's the HRT prescription. And then later it was realized that you can actually compute corrections in powers of G Newton, or if this is CFD, in powers of 1 over the central charge of the CFD, to this formula by also including the entropy of the bulk. So you don't just look at the area, but you consider this quantity called the generalized entropy, which is given by the area over 4G plus the von Neumann entropy of the bulk matter here. And that's actually a better defined quantity anyway, because there are UV divergences that separately would affect each of these quantities. Okay, so now that's supposed to be the thing that computes the entropy of the boundary region. Again, this was first formulated by Faulkner, Lukowitz, and Maldacena for the static case, and then generalized by Engelhardt and Wall for the quantum case. In particular, Engelhardt and Wall argued that you should really, they were actually the first to really point out that this is the relevant quantity that you should be worried about. And that this is also the quantity that you should extremize when finding the appropriate surface. So it's not just that you shouldn't find a minimal area surface and then add the bulk entropy to that area. You should minimize the generalized entropy to find the correct surface. Okay, and that actually turned out to be very important. It underlies the discovery of islands. It wouldn't be possible without that formula. So one thing that I want to start stressing is that for historical reasons, we've sort of been conditioned to think of this as a way of computing an entropy. And it's very nice that you can compute the entropy of a strongly coupled field theory. There's nothing wrong with that. But I don't think that's actually the most important thing about these prescriptions. And that's where the word entanglement wedge comes in. What these prescriptions are really telling us is which part of the bulk can be reconstructed from a given portion of the boundary. If I'm interested in finding a CFD boundary operator that can implement this quasi-local operator here in the bulk, well, I can do that if this bulk operator is within the entanglement wedge that I just found by this prescription. And I cannot do it if the bulk operator is outside of it. So I think we should properly understand these prescriptions as telling us about subregion duality in quantum gravity. It tells us if we're given some portion of the quantum gravity theory, which part of the space-time geometry we can learn about from that portion. Okay. And it's just sort of a byproduct that also allows you to compute the entropy of your quantum gravity theory associated with that bulk region. And that's one thing I want to stress. The other thing I want to stress is that while this is historically very strongly tied to the ADS-CFT correspondence and was discovered in the context of sort of trying to understand its dictionary, in hindsight, that's purely a historical accident. This should have already been clear. I think it was clear to Lukowitz and Maldacena when they proved the Ryu-Takeyanagi formula, which I don't know, was maybe in 2013 or something like that. Ryu-Takeyanagi was in 2006. So it's been, some people have known this for a long time. The point is that you don't need to know what this quantum gravity theory is. In this case, it's a CFT, to derive this formula. You just need to know that there is one, and it has a quantum state whose entropy exists, right? And then you can try to compute the entropy of this quantum state by computing the Renyi entropies. That's basically just computing things like trace quantum state to the nth power for all integer n, and then doing an analytic continuation to n equals 1, and that gives you the von Neumann entropy. And you can do this using the gravitational path integral, which is basically semi-classical gravity. So you don't really know the full quantum gravity theory. You just write, n copies of the quantum state on the boundary, and then you fill this in with a geometry, and you do a saddle point approximation. And then there's a very elegant way of continuing to n equals 1, which basically just becomes the RT prescription. Just what you could have done in the first place is just find the minimal area surface anchored to the boundary. Okay. None of this involves any appeal to any specifics about the ADS-CFT correspondence. It's a completely semi-classical statement. Okay. And as a result, it should really be true in other spacetimes other than ADS, like maybe the universe we actually live in, or maybe asymptotically flat space. In any other spacetime, the basic set of arguments that Lukowitz and Maldacena used should apply. We can certainly make sense of this concept of minimal surfaces or extremal surfaces in arbitrary spacetimes. Well, I think one thing that obscured this fact for a long time is that in spacetimes that are not asymptotically anti-de Sitter, there aren't actually a whole lot of minimal surfaces that you can anchor to the conformal boundary of the spacetime. In de Sitter, there aren't any, pretty much. And yeah, asymptotically flat space, there aren't really any either. So there seem to be a lack of examples by which to illustrate this generality. Right? That changed when Pennington and separately Almeri and Merolf, Maxfield, and Engelhardt discovered this concept of entanglement islands. That in some cases, the smallest generalized entropy region that's homologous to a given boundary region can contain a disconnected piece. In particular, this happens for a black hole when it's more than half evaporated. So you've got your black hole, it's emitting radiation. Maybe we absorb this into an external system, and we ask what is the entanglement wedge of this external system. And after the page time, when more than half the black hole is gone, this will include an island in the interior of the black hole because it's worth paying this price in area because you decrease the entropy by more than that after the black hole is more than half evaporated. So this thing is called an entanglement island. And as you see, it's not connected to the boundary. It's just a disconnected component. And those things exist in asymptotically flat spacetimes. They exist in a universe like ours. If you actually had a black hole and you collected its Hawking radiation, then after the page time, that Hawking radiation would have an entanglement island inside the black hole. And including that in the formula correctly computes the so-called page curve. It actually gives you the correct answer for what's, for the answer expected from unitarity for the entropy of the Hawking radiation. Okay. So that's nice. And it really brought home, at least to me, finally brought home the point that these formulas for the entropy and more generally the concept of an entanglement wedge, therefore, are not tied to ADS. Okay. But then what are they tied to? Are they tied to the boundary? Well, let's go to our universe. Well, our universe, at least on some scales, can be approximated as flat. We could have a small black hole that's evaporating into a region that's smaller than the Hubble scale. And so then this Hawking radiation would arrive here at what we might approximate as conformal infinity, or scribe plus, of this asymptotically flat space-time. And we could then ask, what is the entanglement wedge of this portion of the conformal boundary? And after the page time, it would include this island. That's very nice. But there's something very unphysical about having to appeal to a conformal boundary. It shouldn't really matter if we ask about the entanglement wedge of the radiation once it's infinitely far away, so long as it's just really far away. We should be allowed to ask what is the entanglement wedge of this bulk region here. But now I said it, right? I'm asking about the entanglement wedge of a bulk region, not a boundary region. Because I can certainly have bulk regions which are as good as a boundary region. Okay, so I'm trying to take you on a slippery slope here. Once we agree that there should be an answer to what's the entanglement wedge of the Hawking radiation when it's only finitely far away, it should be the same answer as if it's infinitely far away. Well, then, where do we stop? You've already allowed me to ask about the entanglement wedge of a bulk region. And more generally, when we remember what was the entanglement wedge in the original context, it was a bulk region that could be described by some portion of a quantum gravity theory. What's the analog of that in the question that I just asked? I said you don't need to know what the quantum gravity theory is to compute what the correct bulk region is. So by asking this, we're basically saying that a gravitating region can know about other gravitating regions in an appropriate sense, which I think we'll have to understand better. But let me now go into trying to come up with, a better, more systematic motivation for what I just claimed should be true. And then actually make a proposal for what the entanglement wedge should be of a bulk region. So let's start. I think I already made this point. When a black hole evaporates, there's really no point in waiting until the radiation is somehow formally at infinity or outside of the space-time. It's a very unphysical thing anyway. If I have some distant region contains the radiation, its entanglement wedge should be a meaningful concept, and it should contain the island after the page time. Okay, so that's one thing we want. Another motivation comes from tensor networks. So in the context of ADS-CFT, we learned that tensor networks are a surprisingly good model for understanding the bulk-to-boundary map. You can have little sort of bulk legs that feed in a bulk state, and then there's a tensor network that produces a corresponding boundary state, and you can understand things like why you can reconstruct certain parts of the bulk from certain parts of the boundary very directly in terms of sort of minimal cuts through the legs of this tensor network. But there's nothing about those statements that's specific to going all the way out to the boundary. I can draw you a piece of a tensor network that looks like this and argue that just as a matter of mathematical fact, that if I use the tensor network to move the state, this bulk leg, into this region here, so across this boundary, I basically only act with this tensor and not yet with the other ones. Then I can take a bulk state that comes in here as well as whatever comes through here and define an isometry, in other words, a map that takes orthogonal states to orthogonal quantum states, in which this state now lands over here. Think of these legs as the output legs and this dot and this leg as the input leg. It's not really important that the tensor network keeps going over here. it's something that's sort of locally true in a tensor network. You don't have to go all the way to its edge. Right? You can sort of push quantum states through it. So that suggests that we could do this for bulk regions if this analogy survives. One thing that wasn't originally a motivation for me, but which I felt fit in really well, was when I learned about work by our very own former grad student, Chris Akers, and Jeff Pennington, which is being generalized by Liz and Adam Levine and Akers and Pennington, where they came up with a very concrete and operational way of thinking about how the information from the bulk is moved to the boundary. And they related it to a concept from quantum information and quantum communication theory, which to me was completely obscure, the notion of state merging, and more specifically, and I'll come back to that at the end, one-shot state merging. So in communication theory, you care about how you compress a message efficiently. You know, and Shannon entropy is relevant to situations where you send many copies. So for example, when we send a text message, that's many copies of letters. And those letters don't all have equal probability. And because there are many of these letters that are sent, we can really reduce our message code to sequences of letters which are particularly common. And that's what the von Neumann entropy measures. It basically tells us, you know, instead of log 26 per letter entropy, we only need, you know, the von Neumann entropy in terms of cost of sending this information. I understand this is how compression on a computer more or less actually works. So that's very nice, but for that kind of compression to be possible, you need to be in a situation where you're sending many copies of, you know, variables drawn at random from the same probability distribution. Okay. Sometimes you send only one copy. Like if I want to send you one letter, I can't compress that, right? There are 26 possibilities for what I might need to send. And so I don't get to use the von Neumann entropy to quantify the cost of that communication. But in some cases, you can still compress some approximate way. For example, maybe there are some letters that have exponentially small probability, and I'm willing to take that risk that it's one of those. Then, you know, I get to remove those from my code. Well, that's what these guys were thinking about. They were arguing that the way ADS-CFT actually works is the entanglement wedge is the largest region such that, oh, I haven't told you what state merging is, but such that state merging is possible across any part of this region towards the boundary. So let me tell you what state merging is specifically. It's just a way of coming up with specific rules for the communication. Okay. Suppose I have in this region here a bunch of matter which is entangled with a reference system R that's auxiliary. This is just so I don't have to talk about mixed states. I want to have globally a pure state. So if these are mixed, then I'm just going to add a reference system R that purifies them. Okay. That's not the only entanglement in this region with the rest of the world. There's also entanglement across the boundary of its region that we usually quantify in terms of its area, but we can also think of as the vacuum being entangled across this surface here. Okay. So let me call the other side of this blue region here R prime. These basically just act as reference systems, and the blue region has the property that it contains the purification of these reference systems. It purifies R prime because, you know, it contains the other side of this dividing surface, and it purifies R because it contains some matter that happens to purify R. And the task of the state merging protocol is for Bob, who lives in the blue region, to move all that purification of R and R prime over to Alice, so that now Alice holds the purification of R and R prime. Okay? And for that, you need some resources. It's like with teleportation or something. I can send you a qubit. If hold at least one qubit of entanglement, or E-bit, right, I can burn up that entanglement, use quantum teleportation, and I can send you my unknown qubit. Okay. So similarly, Bob can send his purifications to Alice if he's given appropriate resources. And let's say we think of this area here as a resource. This is indeed, if you think of the vacuum being entangled across this surface that divides Alice from Bob, the amount of entanglement, or E-bits, that I have here is indeed given by the area of this surface. So let's think of that as a resource for moving the entanglement over to here by some protocol similar to teleportation. Okay. And this will clearly be true in simple cases, right? If this area is at least as big as this one plus this entropy, right? Because what we need to do is basically take these lines and carry them over to here. Right? And so this is how much resource we need. We need this area, this red area, big enough. Okay? So going back to ADS-CFT, if this is some boundary region and you want to find its entanglement wedge, the refinement that Akers and Pennington gave to the old prescription takes into account the fact that sometimes moving this entanglement over to A is harder than you thought because you have to do it as a one-shot process. And in the past, people hadn't considered these weird quantum states where that makes a difference. Okay? And so the definition that they gave, which reduces to the old one pretty obviously, is that the entanglement wedge of B is sort of the largest region. You're trying to push this blue region as far over to here as possible. That has the property that when you then pick an arbitrary red surface that divides this into a homology region closer to the boundary and one away from the boundary, that you can do state merging across any such red surface. If you could do it for this one, well, then maybe let's try to push this blue region out a little more and try again. And when you start failing, that's where you have to stop. Okay. So that's what's called the entanglement wedge. And in fact, there's a fine distinction here. There's actually a max entanglement wedge and a min entanglement wedge. Because of these one-shot protocols, there's two analogs of the von Neumann entropy called the smoothed min entropy and the smoothed max entropy. And I'll come back to that again. Right now, I just want to stress that the final result of this state merging protocol is always that you've moved the bulk state to a bulk region, closer to the boundary for sure, but it's again a bulk region. To me, again, this really supports the idea that what holography is, it's not a relation between some boundary and the bulk. It's a relation between one bulk region and a bigger bulk region, where we are in some way allowing a larger algebra to probe the quantum state in the smaller bulk region to make up for the fact that it's smaller. In particular, in this case, all of this information lands right here in these sort of UV modes that are entangled across this surface and which we don't usually include in our effective field theory. So this balances out the fact that this region morally shouldn't contain the same information as a larger region. We're appealing to some degrees of freedom which we didn't appeal to when we were discussing the entropy in this larger region. Okay. In particular, what we'd like to be true, right, is if we define an entanglement wedge for bulk regions, then in this particular example, where A is one of those bulk regions that can receive information by state merging, we want it to be true that the entanglement wedge of A pops us back out to the entanglement wedge that Akers and Pennington defined. And then finally, this isn't so much motivation as a check in the end on our proposal. You know, the reason that we think the entanglement wedge corresponds to some actual quantum state in a quantum gravity theory is that it has properties that you would associate with a quantum state, which is not trivial. So in particular, the generalized entropy of the entanglement wedges of three boundary regions obeys an inequality that's normally associated with quantum states associated with three independent quantum systems, namely strong subadditivity of the von Neumann entropy. So we'll want to show that an analog of that statement holds. This has been proven for entanglement wedges of boundary regions, of course, but we need to check that it will hold for the proposal that we'll make. Okay. In addition, we want some sensible properties like the entanglement wedge of a bulk region should contain that bulk region itself, since we already have access to it by definition. If I increase the size of the bulk region, I would expect that that should increase the size of the entanglement wedge. That's called nesting. That's certainly true when you're dealing with a boundary region. You have to be careful, though, because for boundary regions, it's true that the boundary region and its complement are independent quantum systems. This is not true for bulk regions, and that leads to some subtleties in the time-dependent case that I might have time to discuss. But basically, we want this. We want nesting. And then finally, we want an analog of complementary reconstruction or complementary recovery, as you would call it in quantum error correction. In the ADS case, right, normally it's the case that if this region here is the entanglement wedge, if little b is the entanglement wedge of big B, then the entanglement wedge of the complement of big B on the boundary will simply be the complement of little b in the bulk. This is not true for all quantum error correcting codes, but it is true modulo the subtlety that Akers and Pennington found in ADS-CFT. And in particular, you can't have overlaps. The thing that would be really terrible, right, is if the entanglement wedge of B contains some piece that's also in the entanglement wedge of B bar. Because then I could basically quantum Xerox or clone this quantum state here and move it to both parts of the boundary, and that's inconsistent. So we want no cloning. If B is outside if B is not in the entanglement wedge of A and A is not in the entanglement wedge of B, I want the entanglement wedges not to overlap. So we'll be able to verify that all those properties hold. Did you have a question?
Oh, no, not correct. Because you said that ADS-CFT, it's a complement. It's only for pure state.
Yeah.
Because this never happens.
Yeah, this never happens, yeah. Yeah, so in ADS-CFT, what can in fact happen is that the entanglement wedge of B bar and B have a gap, like this, and I'll get back to that. Even if we have a pure state, this can happen thanks to the observation of Akers and Pennington. Okay, so here's the proposal. After all this, the proposal is actually very simple. It's so simple because I'm going to restrict most of my discussion to a time-symmetric Cauchy surface. So, meaning it's momentarily static. Okay, so this could be a universe that was expanding and it's about to recollapse, and we're at the moment of the turnaround time, for example, right? Or it could be the t equals 0 slice in Minkowski space. Let's say it's that. That's the easiest thing to think about. So let's say A is this sort of crescent-shaped region at my t equals 0 slice of Minkowski space. Our prescription is that the entanglement wedge of A is simply the smallest area or smallest generalized entropy, to include quantum corrections, region or wedge that contains A. So in simple cases, that'll be the convex hull of A. You can think of it that way. It's not necessarily the convex hull, because sometimes you can get to a smaller area by forming the convex hull separately of these two pieces. Let's say A is the union of these two guys. The smallest area region that contains both is actually still disconnected. If I bring them closer together, it'll be connected. So that's the proposal. If A contains the radiation that's entangled with some region behind a horizon, and so long as this region is closed off by an area smaller than the entropy in it, then the entanglement wedge of A by this prescription will include this island. So are there any questions about the definition? That's kind of that went very fast, but there's nothing more to say about it. That's the whole proposal for static for this. So this is sort of analogous to the Faulkner-Lukowitz-Mardasena quantum generalization of the Ryu-Takenagi proposal. Everything is static right now. We're not allowing time dependence.
This was kind of assumed when we do the analysis in cosmological
You mean like in Hartman's work, where he was worried about?
Or even associated computing what's the entanglement entropy associated with certain region.
With what region, though?
Or certain region, but it's not at the boundary, but in the bulk region. Putting gravity.
So yeah, I'm sorry, but yeah, I wasn't aware of the fact that people considered the question of what the entanglement wedge of like some arbitrary region in, let's say, the Sitter space is.
Oh yeah, even in flat space black hole or something, without actually thinking the path switching off the gravity, and gravity is still there, but it's weak. Then that's a kind of right. It's assumption.
So yeah, so there's a paper by Xiaolang Xu and Xidong and two other people that I can't remember right now, who are not quite doing this. So in particular, what our proposal will do is, so they were interested just in getting the island. So suppose that I consider this is ADS, and I consider this boundary, this near boundary region. So this is a bulk region, just happens to be near the boundary, right? So our prescription will tell you that the entanglement wedge is the entanglement wedge that you would have associated with the boundary region that it's adjacent to. Their prescription will not. It just freezes this region, asks if it happens to have an island or not. So yeah, so it's a little different from that. Good.
Raphael, I think generalized entropy is well defined for like a boundary region and for black hole, but I think it's difficult to calculate the generalized entropy for arbitrary subregion because, for example, if in a black hole we can from the set point of the time interval, we know the generalized entropy will be the area term as the net field contribution. So how can we calculate the generalized entropy for arbitrary subregion?
I'm afraid I didn't fully understand the question just acoustically, but
I mean, for example, if we consider a boundary state, the generalized entropy can be read as area term plus the contribution from the magnitude field.
yes,
But for arbitrary subregion, bulk subregion,
yes.
how can we calculate the generalized entropy?
Well, so the generalized entropy is supposed to be defined as, so there are subtleties, of course, but I think they arise in a lot of discussions of the generalized entropy in the bulk. You're right about that. But let me just define it here as, so the generalized entropy of some bulk region, B, is given by the area of the boundary of B divided by 4g Newton. And this is at some cutoff, which I could denote with epsilon, plus the von Neumann entropy of the bulk state reduced. So there's some bulk state for the whole bulk, and then you can compute a reduced density operator for the region B. Let's call that rho B, which again really involves picking a cutoff because otherwise the entropy will diverge. There's significant evidence so far from a mathematical proof that while each of these terms depend on the cutoff, there's some does not. And so that's the definition of generalized entropy that's being used here.
Yeah, right. I have another question. In ADS space, you can let the subregion to be near the boundary to verify the correction of this definition. But if in a general space-time, how can you verify if definition is good?
Oh, the definition is a guess. What I'm telling you is that it satisfies a number of properties that would seem an awful conspiracy for them to be true if the generalized entropy of these regions did not represent the entropy of some actual subsystem of a true quantum system. So the thing that's so surprising, right, about computing the generalized entropy of entanglement wedges in ADS, well, if I hadn't told you about ADS CFT, right, but I'd given you the Ryutake-Yanagi prescription or its generalizations, right, then you would have started to realize that those areas or generalized entropies, despite involving areas, classical areas, satisfy properties that you expect only of quantum systems, that are very specific, sort of, strong subjectivity of the phenomenon entropy. It's a quantum thing, and it's sort of suspicious that they satisfy it, and you might have been led to believe by this that they actually do compute the von Neumann entropy of some subsystem of a true quantum system, and then maybe after thinking about it for 5 more minutes, you would have discovered ADS-CFT. That's the philosophy here. We don't have a quantum gravity theory, but we have a way, I claim, of assigning an entanglement wedge to a bulk region which has mathematical properties which it really has no right to have unless it also represents a quantum gravity system, some subsystem of a quantum gravity theory.
But the quantum gravity theory, so the quantum gravity theory here would be little a, and the point is that we can compute an entropy that in particular takes into the consideration the quantum degrees, the quantum gravity degrees of freedom of little a by doing a generalized entropy computation on the entanglement wedge of a that doesn't need to know about those quantum gravity degrees of freedom? Is that why it's useful to have E of A?
So E of A, and again, let's go to this alternate history where we didn't discover ADS-CFT, right? Then the entanglement wedge prescription would do 2 things for you, right? It would tell you, so you don't know what the boundary theory is, but it would tell you, given a certain part of the boundary, what it describes in the bulk. And it would also tell you, given a particular bulk quantum state, what the entropy of the quantum state of the unknown boundary theory is. You would still not know what the boundary theory is, but you'd get a bunch of very interesting information that might help you find it. That's the claim. I can't guarantee that that information is enough to find it. But yeah.
Right, so what is confusing me here is that in that picture, the boundary theory naturally lives another theory different from the bulk gravity theory. In here, because both regions involved are bulk regions, I don't understand what the correspondence is between two.
Let me invite you to contemplate the following fact. I don't know if that'll help. But consider the algebra of operators in the CFT associated with a particular boundary, causal diamond, or whatever, right? That algebra is generated by the local operators in the CFT. If I give you all of those, you can just take products and so on and generate the full algebra, right? But those local operators are in one-to-one correspondence with quasi-local operators very close to the boundary in this region little a. So this region little a actually, it's not so different from the CFT out here. If you take the local operators that we have control over in an effective field theory description, and you sort of blindly generate a full algebra from them, what you're going to get is the boundary algebra. But again, I am not making a claim that we know what this result means in detail. All I'm trying to say is that it is possible to, and I haven't quite shown this yet, but it is possible to define a larger bulk region given a smaller bulk region that has all the mathematical properties that we see in the entanglement wedge or at least all the important ones that we see in the entanglement wedges in ADS-CFT. And then, the rest. We'll see what happens. So showing that E of A contains A is trivial because we made it part of the definition. It was supposed to be the smallest generalized entropy region containing A. And it's not hard to see that. By the way, let's give a name E to this entanglement wedge of bulk regions in the static case, big E. Then it reduces to EW, which was the name for the entanglement wedge of a boundary region. In those cases where little a, the input to this map, big E, is near the boundary and is contained in the entanglement wedge of the boundary region, then the entanglement wedge of this bulk region will be the same as the entanglement wedge of the bulk boundary region. that just follows from the fact that the Ryuta-Kiyanagi proposal says the same thing as our proposal in this case. No, cloning is a little bit more interesting. So here are two regions A and B. They're both in the bulk. And let's say that this is E of B, according to our prescription, the entanglement wedge of B. And this thing here is the entanglement wedge of A. Now, this is a situation where B is outside of the entanglement wedge of A, and A is outside the entanglement wedge of B, which is about the, which is the correct requirement for being able to say that those two should be independent degrees of freedom, even at the quantum gravity level. In quantum gravity, of course, you have a high degree of non-locality, but that's sort of what you want to require so that they can be treated as independent. In that case, you don't want to see their entanglement wedges overlap like I just showed. That's sort of this no cloning requirement. You shouldn't be able to pull some information from this region both to little b and to little a and thereby clone a quantum state. And to see that our prescription satisfies no cloning, what you do is you assume that this bad thing happens and you derive a contradiction. So the thing you want to consider is basically the entanglement wedge of A with this little overlap region removed. So that's this object here, EA without EB. And then the same thing for EB without EA. And it's not hard to see by seeing how the areas add up, work out, and using ordinary subadditivity for the quantum states in these bulk regions, that the sum of these two slightly reduced entanglement wedges the sum of their generalized entropies must be smaller than the sum of the original EA and EB generalized entropies, which means that by removing this overlap region, I must have reduced the generalized entropy of at least one of these two. Otherwise, it's impossible to achieve this. Okay. But each of these reduced regions still contains the input region, A and B. And so that's a contradiction, because those were supposed to be the smallest generalized entropy regions that contain A. At least one of them is not the smallest. That's it. And then strong subadditivity of the generalized entropy of these entanglement wedges. Well, again, you have to appeal to just geometry. You figure out which area pieces can be moved around to where, and strong subadditivity of the ordinary matter entropy in these regions, and you can derive from that the strong subadditivity of these entanglement wedges. So it has the properties that we really want it to have. Oh, there's one more. Sorry, nesting. So sorry for the Greek letters, by the way. We changed conventions at some point, so this is still old figures. This is A and B, obviously, right? So we don't want it to be true that the entanglement wedge of A fails to be contained in the entanglement wedge of B. That would be bad. We kind of think, okay, if we make the input region bigger, we should be able to have strictly, more access to the world, not less. And again, you can show that if this happened, you'd have a contradiction, namely the generalized entropy of so you observe, first of all, that A being part of B is not only in the entanglement wedge of A, but also in the entanglement wedge of B, as is already correctly drawn here. Which means, since the entanglement wedge of A was supposed to have the smallest generalized entropy, its generalized entropy has to be smaller than the union of these two entanglement wedges. Than the intersection of these entanglement wedges, and the generalized entropy of B has to be smaller than the union of the two entanglement wedges. So that's one side of the argument. Then you use the usual moving around surfaces, counting them up, and ordinary strong subadditivity to derive the opposite inequality. And so again, you have a contradiction unless equality holds, which eliminates this piece that sticks out. Let me stop here for any further questions before we talk about the covariant case. Yeah.
Can I ask a naive question? So just quantum mechanically, I'm trying to think how I am supposed to think of some of these quantities as being defined. So like, is A an operator, or am I in a semi-classical limit? Or?
Yeah, good. So A denotes a spatial region, or in the time-dependent case, you really want to think of the domain of dependence of the spatial region, so some kind of wedge in space-time. And the quantum state that goes into computing the generalized entropy of such a region is defined in the sense of quantum field theory on a fixed background by identifying the quantum state of the full space-time, reducing it to this region, and then computing trace rho log rho.
Okay, so A is not like an operator.
A is not, no, yeah, A is, that's right. So this is, this is what's so weird about the Ryutake-Nagi proposal, but it was already weird about Gibbons and Hawking computing the thermodynamic entropy of a black hole in a thermal state. It's that you can use effectively techniques from quantum field theory on a fixed background together with very primitive techniques from of basically applying a saddle point approximation to the quantum gravity path integral to extract information about quantum gravity degrees of freedom that, that has no analog in theories other than gravity. Small classical gravity knows something about its own quantum states and those of matter. Yeah, that's right. Thank you. Yeah, so this is what was in that paper that already came out. We struggled a lot with a covariant generalization of this proposal. And I think now we have it, so I'll tell you a little bit about it. Though not everything, because there's not enough time. So by covariant generalization, I mean the analog. Let's say, so RT is sort of the simplest thing. You just worry about the classical areas, and you have a static situation. HRT generalized that to a dynamical situation, still just worry about areas. FLM included quantum corrections, and the generalization of that was done to the dynamical case was done by Engelhard-Inwald. Okay, so we're trying to do the analog of that arrow here, okay, for our prescription, and we can again, of course, it has to have the property that's consistent with what I've just told you, so it has to reduce to the static prescription I just gave you, and for the purposes of this talk, I'll just discuss the classical limits. I'll basically discuss the analog of RT goes to HRT. Won't even worry about quantum entropy right now. Okay? So here's why this was hard. It was hard because nothing works. Okay? So the first thing you could try, if you really don't remember anything, is let's say that the entanglement wedge of some bulk region A in the time-dependent case is the same prescription that I just gave you for the static case. Smallest area wedge that includes A. Let me say why explain why I'm using the word wedge rather than region now. By wedge, I sort of mean the domain of dependence of some spatial partial slice, some piece of a Cauchy slice. And when we worry about inclusions, now we have to worry about basically these whole wedges, including, or if I have a wedge and I want to know what its entanglement wedge is, well, I want that entanglement wedge to include its original wedge, so it might be something like this. Right, so this could be the entanglement wedge for A. Let's give it a name, little e of A. Just think of it as a space-time region that's sort of diamond-shaped. Okay, so this doesn't work, right, for this annoying wiggling reason, right? I can give you any input space-time A, whatever its area is, doesn't even matter, and I can surround it with a region that has arbitrarily small area and is arbitrarily close to A. So this isn't even well defined. The smallest area which doesn't exist in the dynamical case. So that's shown here. Another stupid idea is to say, well, okay, let's be more, more restrictive. Let's say we want the smallest area extremal surface that includes A. But that wouldn't work because it doesn't reduce to the static prescription. Remember that in the static prescription, we could have some crescent-shaped region at t equals 0 in Minkowski space, And the entanglement wedge was just the convex hull of that. And yeah, it's extremal right here, but it's still normal there. So this, again, doesn't exist in general. That you wouldn't be able to find the smallest area extremal wedge that includes A. OK. So next stupid idea, which we actually pursued for a remarkable amount of time, before we noticed it doesn't work, is let's say E of A is the smallest area normal wedge that contains A. Say normal includes as a special, so normal means, sorry, I should say this, normal means, if I have a ball-shaped region in Minkowski space, you look at the outgoing light rays both towards the future and the past, the area increases in those directions, then you call it normal. And this is sort of defined point-wise at every point on the boundary of the region. So that's a normal region. Anti-normal would be the opposite of that. And then there's trapped and anti-trapped that kind of completes the story. So we tried that because it would allow both for this normal part and for this part in the static case. We'd be all right. And it actually seemed to work until it didn't. And it was fairly, normally when something doesn't work, it's not that hard. Like in these other examples, you notice pretty quickly that it's nonsense. This was really hard. Like to find a counterexample, you cannot use spherical systems, for example. You have to use non-spherical examples. And you have to, so you have some ugly systems or regions that don't satisfy strong subjectivity. So.
And it's not like this is what we're doing like a pre-mean procedure. If you put like external surface for each one of the regions, and you kind of put in. For the boundary you can do, but it don't need to be boundary. So
I'm not. What is the proposal you want to examine?
Small external surface for any region, you can think of small external surface. From
You mean
edge of the A.
You want to surround this by pieces of extremal surfaces, like this?
No. If you take any small region and then you consider external surface anchored to any small region of the boundary of A. Consider del A.
Yeah.
And then you divide it into a very small region of del A.
But I can't. I have my input is a region, not a part of the boundary. No. Trust me, nothing works. This took a while. I certainly went around in circles over and over again trying to come up with a good definition that does all the things we wanted it to do. And I can prove to you that we couldn't come up with anything that worked.
Did something similar.
But then it occurred to us that we might be asking something too strong of our entanglement wedges. The reason that this is a little bit surprising and we didn't think of it right away is that the thing that's too strong is that there is one entanglement wedge rather than two. I mentioned this early on in this talk, that when Akers and Pennington were worried about corrections to the Ryutake-Yanagi proposal that had to do with the subtleties of one-shot quantum communication and one-shot entropies, that they ended up defining two entanglement wedges that they called the max entanglement wedge and the min entanglement wedge. The max weirdly always being contained inside the min entanglement wedge. It's the smaller one, but that's because it's based on the max entropy, which is the bigger entropy. Never mind. This seemed to be, in my mind at least, associated with the weirdness of extremely strange quantum states that normal people don't usually worry about. And so it didn't seem to, it wasn't clear to me why this would play a role in our prescription or in our search for a prescription, so long as we didn't consider these weird kind of incompressible quantum states. Okay. I think I already said most of this, so let me just skip over it. I said this kind of at the beginning. But here's the upshot, right? Complementary reconstruction fails when those two entanglement wedges that they define don't agree. So they, of course, define them for boundary input regions, the old-fashioned way. And then sometimes you can have a gap, even if the boundary is in a pure state. This blue thing here might be your max entanglement wedge for the region B. And this green thing would be the max entanglement wedge for the region B bar. And they don't fill up the space-time. And in the boundary case, it is true that the min entanglement wedge of B is the complement of the max entanglement wedge of B bar. So this picture really shows all four of them. Okay. So that's true when you consider these weird quantum states. They live here in the gap. Okay. When that happens, it's also not true that you can even ask about strong subjectivity. Okay. Strong subjectivity holds only if the min and the max entanglement wedge are the same for all the relevant boundary regions that go into the formulation of the statement. Okay. But again, this gap that leads to these weirdnesses arises only when you consider these weird kind of quantum states that normal people like us don't even normally know about. What we've concluded is that with bulk input regions, this distinction between a max and a min entanglement wedge arises already at the classical level. You don't even have to include any quantum corrections. It already arises when you're just worried about area. And let me give you the prescription that we're proposing for this classical limit. So the max entanglement wedge we propose is the smallest area wedge that contains A, and which is extremal except at A. So if this is your region A, then if this is a nice normal boundary, near boundary region that I didn't wiggle, then of course the entanglement wedge, both the min and the max entanglement wedge would be the one you expected, the one that's also the entanglement wedge of the boundary region. But if I wiggle it, then a distinction appears. Because, did I formulate this correctly? I didn't. I forgot a piece, sorry. This definition also requires for the max entanglement wedge that the max entanglement wedge must have area smaller or equal to the area of A. That should have appeared as part of the requirements here. If I wiggle this red line up and down in time in a way that I can't show here, I can make its area essentially 0. And then the only way that I can find a wedge that satisfies this is to take the max entanglement wedge to be A itself. Because this one here, which is extremal, has non-zero area. It's too big. Okay. But the min entanglement wedge is defined as the smallest area wedge that contains A and is extremal everywhere. And that's the usual entanglement wedge of this boundary region. So now there's a gap. Okay. Similarly, if I let A, so this is a two-sided black hole, maybe with some matter around, so the horizons aren't necessarily null, the apparent horizons. So I let A stick into the black hole. This is a trapped surface. Okay. The max entanglement wedge in this case is again A itself, because if I move out here to find a surface that's normal or extremal, I won't succeed. In fact, even the nearest normal surface, okay, I wrote this at the last minute, and so I should have been more careful. Instead of extremal, I should have said normal here in both of these cases. The smallest normal wedge that contains A has really big area compared to A. Right? This area could be close to the singularity. It's very small. This sphere is much bigger. It's on the horizon. Okay. So again, there's a gap, in this case, this area here in the this space-time region, between the max and the min entanglement wedge of A. What can we prove about this prescription? As the one where I actually write down the correct prescription. Sorry about that. We can prove that the min entanglement wedge always contains the max one. It's always bigger, just like in the boundary case. The min entanglement wedge obeys no cloning and nesting, just like in the boundary case. But the max entanglement wedge does not obey nesting. That's the thing that we had to give up. And that's kind of why we spent a huge amount of time trying to find something that probably doesn't exist. Here in this example, you see this. The max entanglement wedge, if I wiggle this surface, doesn't obey nesting because I could find a subregion of A that's even closer to the boundary in which I didn't wiggle the surface, but that's fully contained in A, and which would have this big max entanglement wedge that goes all the way out to the blue line. So the max entanglement wedge does not obey nesting. In hindsight, that actually should have been not so surprising. The way we were thinking about it, I think incorrectly, is to say, well, you got to have nesting because, look, if some subregion of A has access to the information out here, then how can it be that A doesn't? But when I described how the information is actually piped into A, it's kind of teleported to just inside this surface. You're using this area as a resource to move the information into A. So if you've reduced the area, making it almost zero, that's like crimping your quantum channel. You've produced a bottleneck. It doesn't really matter what A looks like away from this area once you think of the information flowing into A in this manner, where you're basically using the area of the boundary of A as the resource for teleporting it in. So in hindsight, one always knows better. But that's why I think it's okay for the max entanglement wedge not to obey nesting. And after all, we were already okay with these entanglement wedges separately to not satisfy certain nice quantities. Already in the boundary case, we can't ask about strong subadditivity unless they're equal. Same thing here. So if they're equal, then of course they all obey no cloning, nesting, and strong subadditivity. And that's it. Thanks.
Questions, Raphael?
So in ADS-CFT, a big part of it was learning something about quantum gravity from CFT and learning something about difficult quantum field theory from gravity, right? Do we learn something like that from this?
No, this is a totally different program, right? In ADS-CFT, for historical reasons, we already knew, at least in principle, how to compute the von Neumann entropy of a boundary state, because we knew what theory it was, and we knew how to figure out which state we should use to describe some particular bulk state. In practice, of course, it's often hard, but because it's a conformal field theory, we actually do have techniques for computing its entropy directly, right? And this is how Ryo and Takeyanagi wrote their paper. They immediately checked their proposal by actually computing the entropy of the boundary theory independently. We can't do that here, right? We don't have the boundary theory, and it would be therefore we cannot compute any entropy independently. So this is a situation where, again, for me it helps to imagine what if RT had been discovered before ADS-CFT, and it would have been interesting to have a prescription that lets you compute the entropy of an unknown quantum gravity theory, and it might have helped us understand how to find that quantum gravity theory. It's hard to know. I mean, it's an alternative history, but that's the situation that we would be in with this proposal. We don't have the theory, but we can use this prescription to at least access certain small aspects of it, like how big. In some sense, there's a quantum gravity theory that lives at the boundary of any spatial region, and you can ask how big is the bulk region beyond the input region that theory describes, and what is the entropy of the quantum state that's associated with that.
Does this give us any direct insights into quantum gravity in de Sitter space? Thought about that specific case.
A little bit. I, you know, as you can see from the poor execution of the last or second to last slide, the covariant case is a fairly recent development from like less than a week ago. So I've been spending most of my time just kind of checking that it really does all the things that I claim it does here. And I haven't, you know, given myself the luxury of playing around in the sitter space with it, but hopefully it'll be fun.
That's what I wanted to say for my first comment.
Yeah, yeah.
Because in this eternal inflating space, I took this vision up.
Ah, you mean the multiverse?
Yeah.
Sorry.
And then, yeah, of course, it's the same level. It's only you know, island aspects of it. But if it's a kind of convex region, then of course it's a special case. What is there? The claim is the same. You have to find some region which include this R, which minimize. And in that case, it's extreme prescription is good enough because it's already convex.
Yeah, exactly.
So that's what I meant.
Yeah.
So
Yeah.
yeah.
I'm sorry, I thought you really meant the sitter space, just like one cosmological.
The sitter case we can do with an open or something. It's a similar. Again, it's pretty coupled.
Okay.
Coupled region and so on. And yeah. Then you have to complicate it slightly, dosita, close dosita or something. But because pure dosita doesn't have same ion.
Yeah, in the sitter you're not going to find an extreme surface.
You have to do some complicated stuff.
Uh-huh.
Other questions, Raphael?
Yeah, I'll ask one. At the beginning, you gave us some motivation from like tensor networks. Are you imagining that if this formula holds in spacetimes that aren't asymptotically flat, that like the general spacetime can be modeled by some tensor network?
Well, I think that I used to be very pessimistic about tensor networks. That, you know, it just seemed like they were so tied to these sort of static examples of Ryutaka and Nagi, and didn't have much of a chance of being relevant for fully dynamical situations. And I think we don't know a whole lot about how it's supposed to work in dynamical situations. I mean, when Aaron Wall came up with this Maximin prescription that picked out certain classes of bulk slices, that I think helped the situation a little bit because you could imagine the tensor network lying on that particular slice. I mean, the problem with the tensor network is always that it's like it's an analogy of a three-dimensional spatial region, right? And then you have to decide how to embed that in your four-dimensional space-time, and in the static case, that's sort of obvious. And here, in general, it's not. And Maximin helped a little bit with that, but it still wasn't unique. You could have a lot of different slices that qualify as Maximin slices. And you know, I think part of the thing we struggled with here is that we also didn't know quite what the rules would be. Like the fact that wiggling this surface reduces the capacity of the quantum channel is, well, it's the outcome of trying to find something that works. And I think it maybe ultimately will help us think about how tensor networks are related to time-dependent situations and this sort of bulk duality that we're proposing. I don't think we could have derived this from tensor networks.
That was my second point.
Good.
Suppose you have some leaf, and suppose you constrain this short region, and then the region which the rest can represent is this bounded by external surface anchored to this small region. Okay, you just mean and then you just convolute these things. This we call holographic slice. You can move in.
Yeah.
And that slice is a particular slice tensor network represent. Okay, so it's not the slice because it just move in. The state is still holographic. Even if you move in, it's still holographic. And you can do this only for some region, and then you can move in a surface. You can take an entanglement wedge. So can you do that? That was my second. Similar thing, you just have, it's pretty similar. It's already gravitating region, and you constrain, you just look at convolution of small external surface, you just move in, and then you have specific slice, and then you take the main components of that slice.
I just don't know, you know, I remember thinking about your construction with, I think this was with Sean maybe?
Maybe with the Chitran.
And definitely,
No, initially with the Kratik.
Oh, yeah.
that we can.
Yeah, so I wasn't sure what to say about this situation here, and in particular how to get a distinction between the max and min entanglement wedge. I think it might be closely related to the max entanglement wedge, and we weren't happy. I mean, I think you can't be happy here without all. If you just had the max entanglement wedge by itself, right, you would not have nesting, you would not have strong subjectivity. It's the fact that you also have a min entanglement wedge and you can ask the question whether they're equal that lets you recover these properties. But I think in hindsight, the max entanglement wedge is probably closely related to your construction.
But I think we could prove all these properties, nesting and
yeah, then it's
of course in the case of only convex space, so this is something only inside, right?
Yeah.
But inside you can move in, and we could show that that procedure would.
Well, these are both counterexamples to nesting as far as the max entanglement wedge goes. So I would invite you to sort of see what the key difference is there. But I'd certainly like this idea of thinking of it as a flow.
Yeah.
Where you sort of keep moving out where you can.
Of course, have to add to some disconnected component. Iron,
Yeah.
it's kind of by hand, but
Yeah.
iron itself is also can be moved out.
Yeah.
To do so that's of course catch. You have to include iron by hand because continuous moving in.
Yeah, but even here, right? If you started with a subregion of this A which had a nice smooth non-wiggled boundary, and you did your flow, you'd end up here.
Yeah, that's what I.
And yet, if you start with this wiggly larger region, you get stuck immediately under this flow. So it doesn't satisfy nesting in the sense that we demand it. There may be other senses in which you don't need that to be true.
Maybe some smoothness condition or something maybe right.
I don't know. Yeah.
That's it possible.
Yeah.
Anything else? If not, let's thank Raphael again.
Thanks.